Okay, so we are going to now, we are now in the final phase of our topic of Fourier transformation. And remember, this topic of Fourier transformation, we started out by uh, looking at the convolution operation. We saw convolution operation from multiple different viewpoints. And then when we started looking at the effect of convolution on complex exponentials, we came across the eigenfunction property of the convolution of a system which implements the convolution operation. And then that led us to Fourier transformation. So now that we are concluding this topic of Fourier transformation, I think it is appropriate, it is altogether fitting that we conclude it by again looking at the application of convolution. Uh, but now that we have appreciated this theory of Fourier transformation in a detailed manner, I think we are probably going to be uh, better able to understand the operation of this linear shift invariant systems which implement the convolution operation. And so the application that we are going to now look at is the noise mitigation in many different scenarios. And this typically is done by means of a filter. So what is that filter? How does it mitigate the noise is what we are going to look at in a conceptual manner. Okay, so there are many cases where at a communication system or even in general, uh, any human man-made or natural source of information may be generating information, but that information may be getting received with a lot of out-of-band noise. Um, one example that we have seen earlier, or actually we have listened to it earlier, if you recall, is the tweeting of a bird. And the bird's tweet sounds, the chirping of the bird, we saw was getting mixed up with a lot of noise, and so we could barely even make out that there was any tweet here. The sound looked pretty noisy. Um, and that this is just an example. I mean, you know, we all know how many times we have been in a crowded room. A lot of people are talking simultaneously, and we are hardly able to make out what the other person is saying. This is especially true when you are talking to someone on the phone, and maybe that person is at a train station or in some crowded area, and the person is trying to tell you something, but you can't make out anything because of the background noise. Uh, there are more detailed scenarios which are not so commonplace examples that I just talked about, but uh, they are nonetheless in our day-to-day lives today. So one example is the cellular phones again. The other example is the television, and the FM radio channels. In all of these different communication systems, the provider of the system, in order to make an efficient use of the spectrum, uh, does not want to waste the allocated spectrum. Excuse me. Sorry. And so, therefore, what they do is they take multiple channels and pack them together next to each other. So, for example, if a particular cell phone provider has many different subscribers, sorry, so they may be assigned adjacent bands, adjacent frequency bands. Um, Similarly, if you look at the entire spectrum of an FM radio system, which is somewhere between 88.5 megahertz to 170.5 megahertz, that is a total of nearly 20, 20 megahertz, about 19 megahertz or so. So in that entire width of about 20 megahertz, almost 100 different FM radio stations are packed right next to each other. And same way, when you get a particular TV channel, that type of allocation of frequency spectrum to different channels is happening there as well. And so now what happens is that when you receive a particular channel, or a particular radio station or a TV channel, um, you are interested only in the part of the frequency spectrum corresponding to the channel that you want to listen to, or you want to get on your TV. But the entire signal has a lot of out of band channels, other signals which are out of this band, and so they act like out of band noise. And so the only way that you can properly listen to an FM radio station or a TV channel, or for that matter, even you can listen to your friend speaking or your relative speaking on the phone, is only if that out of band noise is cleaned up first. Somehow your phone or your TV or your radio has to get rid of all the noise that is coming outside of the band of your interest. And in all these cases, this out of band noise is present in the frequency domain. Remember, all of these channels uh, are channels in the frequency domain. These channels are uh, to be thought of as different parts of some spectrum. And so this out of band noise in all of the scenarios that are mentioned here on this slide, in all these cases it is present in the frequency domain, and that is what we want to get rid of. So the way we can conceptually understand the mechanism by which this noise removal happens is by leveraging the mathematical definition of the rectangular pulse. And we are going to make use of that rectangular pulse to do this noise mitigation. And the way we are going to do that is we'll simply multiply the received signal by a rectangular pulse of some unit amplitude, unit height, and furthermore we will have our pulse of such a width that it completely encompasses the signal of our interest, the channel of our interest, and it is zero outside. And so once we do that multiplication, everything that is outside of that rectangular pulse will get zeroed out because it is getting multiplied by zero. That is what is being shown pictorially here. There is this desired channel or desired band, frequency band, and then there is this unwanted part. And we want to get rid of the unwanted part, so we multiply the total signal, which is the sum of the blue and the yellow, the wanted and the unwanted. We multiply it by this rectangular pulse of unity height, and whose width is exactly encompassing the desired signal. And so now the unwanted part gets multiplied by the zero valued portion of this rectangular pulse, and it just gets removed because of that multiplication operation. This operation is alternatively named as either filtering or windowing or gating. And all of these are common English words. Windowing because you are taking this total signal and looking at it only through the window of this red colored shape. Filtering is again implying that you are filtering out the unwanted portion. It's like you have some let's say sugarcane juice, and that sugarcane juice has not only the juice that you want to drink, but it has the other parts, the shreds of the sugarcane that you don't obviously want to drink. And so before the vendor gives you the sugarcane juice, he filters out the unwanted part of that juice. So the filtering is is a commonly used word in that sense. Whenever you make tea and then drink the tea, you have to filter out the uh, crumbs of the tea leaves. And then finally, it is also called gating because it's as if there is a gate which is shown by this red color, and we are letting only the desired signal come through the gate. We are stopping this unwanted part, and we are not letting it go through our gate. So this is multiple different ways of calling this particular operation, which ultimately is intended to remove this out of band noise. Now, x-axis here in general can either be time domain or frequency domain. It doesn't have to be frequency domain all the time. Um, but if suppose the x-axis is time domain, then maybe it is kind of uh, easy to understand how to do this filtering. We just take the total signal, which is the sum of the blue and the yellow, and then we multiply in time that signal by this red colored signal. So the multiplication operation, which is this gating or filtering operation in time domain, it is kind of easy to understand how to implement. But how to do this gating or windowing in frequency domain? So that is what we are going to now look at. If we consider that this diagram, the x-axis is frequency, not time, then we have to do multiplication of this red colored gate or window with the total signal in the frequency domain. Okay? So that is what ultimately we have to do to get this noise removal by means of this gate or window or filter. The question is how to do this multiplication in frequency domain. Now, there again we go back to the topic that we started out with, which says that multiplication in frequency domain is the same as convolution in time domain. And so, what we would need to do is we would need to take this total signal in time domain and we would need to convolve it with the inverse Fourier transform of this red colored pulse. That will give us this multiplication of the red colored rectangular pulse with the total signal in the frequency domain. Now, what is the inverse Fourier transform of this red colored pulse in the frequency domain? We know that the inverse Fourier transform of a rectangular pulse is a sinc function. And so, finally, we have our answer that to do this filtering in the time domain, all that we would need to do is to convolve the total received signal with a sinc function in the time domain, and the parameters of that sinc function have to be such that the corresponding Fourier transform, this red colored pulse, is nicely centered around desired signal and it has a width equal to the width of the desired signal. And if we do that, then remember this that we had listened to. Now, only if I make it louder, maybe it will become a little more clearer. I'm just repeating what we had already listened to earlier. So you may be able to hear some chirping. And this is the noisy, so this is the original chirp. This is the noisy chirp. You can see that you cannot even make out that there was any birds chirping sound there. But after you do this filtering, you can again nicely hear the chirp back up. And so in the time domain, the chirping of the bird has this type of signal. So this is how it looks like in time domain. If I take the audio of the bird chirping and if I plot that audio, the voltages as a function of time, it has this type of shape. this type of waveform. The chirp is not, the tweeting of the bird is not continuous. It's like the bird makes one sound, then it stops for a little bit, again makes another sound, stops for a fraction of a second. So that the part where it is stopping is this blank dead period, and then where it again starts making sound is where you see this waveform uh, going up and down higher in the amplitude. So this is the time domain uh, representation of the bird's audio when it chirps. And if I take the Fourier transformation, this is how it looks like in the frequency domain. Now to get the noisy signal, what all that I did was I bombarded it with a lot of out of band noise, as you can see. This part, the in band part, I didn't touch. It is still exactly the same as before. But outside of the band, I put a lot of noise, very strong noise. And because of this noise, look at what is happening in the time domain. This time domain signal doesn't look at all like this signal here. It has become completely noisy. But the way I got this recovered signal was, all that I did was, in the frequency domain, I took the total composite signal and I multiplied it with this gate in the frequency domain. And because of this gating, all of this noise got wiped out. It got zeroed out because I'm multiplying in frequency domain. So the noise part of this signal gets multiplied with the zeros of the gate, and so it goes away. So now to summarize, we have to actually uh, do the multiplication of the total noisy signal by a rectangular pulse in the frequency domain. That is how we can get rid of this out of band noise. So that is one option. And the way to do that would be to take the Fourier transform of the actual noisy signal and then multiply that Fourier transform with this red colored window and then take inverse Fourier transform. So that is one possibility. The other possibility, which is completely equivalent, is to convolve the actual noisy signal with the sinc function, which is the inverse Fourier transform of the rectangular pulse. And that convolution operation, we have called it to be a digital system, a linear shift invariant system. And this system has an impulse response h of n, which is the inverse Fourier transform of the rectangular pulse. So it's a sinc function. We take that sinc function, we convolve it with x of n, and then we get our cleaned up version of the input signal. So here I have shown that rectangular gating function in the frequency domain, and it has a certain width, minus zero point 0.2 to plus zero point 0.2 in frequency domain. I am assuming right now discrete time processing. And remember, whenever we talk about discrete time, the normalized frequency has a range of minus zero point 0.5 to zero point 0.5. And so therefore this frequency domain chart, its x-axis is only shown for minus zero point 0.5 to zero point 0.5. Because the signal is discretized in time domain, it is periodic in frequency domain with, and what I am showing here is the fundamental period of width 1 unit. And I am assuming that this gating has to be centered at 0 hertz. It doesn't have to be centered at 0 hertz. For example, over here, the centering was not maybe necessarily at 0 hertz. But as of now, I am assuming that this rectangular gate in the frequency domain is centered at 0 hertz. And It's a nice rectangular pulse centered at 0 hertz, and it has certain width, f of c, which I want to control. This f of c is my important parameter because uh, I want to make it just as much wide as my desired signal. So this f of c is actually uh, this width here, or maybe slightly bigger than the width of the desired signal, uh, just to avoid any problem due to a potential mismatch of the center of this rectangular pulse and the center of the desired signal. Uh, but that f of c is an important parameter. I want to control it very carefully because if I make f of c too small, then some parts of my desired signal spectrum will get chopped off. They'll get zeroed out, which is not good. I mean, I, I would not like to hear a bird chirp if bird's tweeting sound if it's some of its frequency components have been zeroed out. It may not even sound like a bird to my ears. On the other hand, I don't want to make f of c too large, because if I make it too large, then some of that out of band noise might leak in, and it may create some noisy disturbance. So I want to control f of c carefully. But once I decide the value of f of c, then the impulse response of this LSI system is well determined. I just take inverse Fourier transform of this rectangular pulse of width f of c centered at 0 hertz, and I get this sinc function. Remember, this is our Fourier transform pair. So this is what we would need to convolve the input signal with in the time domain to get rid of all that out of band noise in the frequency domain. Basically, the out of band part here is all of these high frequency components. All the low frequency components around 0 hertz are preserved. All the high frequency components outside of that plus minus zero point 0.2 in this case, or plus minus fc divided by 2, they are getting removed. The filter is passing the low frequency and it is rejecting the high frequency. And so that is why this is called a low pass filter. Actually, it should be called low frequency pass filter. A filter which passes all the low frequencies and it rejects, or it removes, or it filters out all the high frequencies. All the frequencies whose absolute value is greater than fc divided by 2, they don't show up at the output. Okay, we will stop here and then continue on this discussion in the next video.